this type of problem, we have we're increasing heat and then changing the temperature, but we're also going through phase changes. And if you remember from before, it takes energy to break attractive forces to allow, let's say, ice to turn into water. And then again, we'll have to break some more attractive forces to get water to turn into steam. And all of that takes energy. So if we're trying to figure out how much heat is required to convert something from the solid form to the vapor form, we also have to calculate how much heat it takes to break those attractive forces and how much heat it takes to raise the temperature. So in this type of problem, you have to think of the heating and cooling curve that we talked about before. Over here you would have temperature. Let's see if I can get that in there. And here you would have energy or heat. And we're going to be adding heat continuously to this entire thing. Now if we're going to be dealing with water, 0 is a very important temperature, and so is 100. Alright, so let's say I start off with ice and I start adding heat. The temperature is going to increase until I hit that 0 degrees Celsius mark. At 0 degrees C, the ice starts to melt. And so it will flatline until all of the ice is converted into water. It's still absorbing heat though, because that heat's going into breaking those attractive forces. Once all of the ice is converted to water, then the temperature will rise again until we get to 100 degrees C, which is the boiling point of water. Boiling water will stay at 100 forever because that heat is being used to break the rest of those attractive forces. Once all of the water is converted into steam, then the temperature will go up again. So we need to think about this graph, and it's divided into 5 different segments so that we can, and we are going to have a math equation for each segment, and then we'll just add them up together. So the first thing you want to do is we want to think of a plan. So in this particular problem, we're going from -5 degrees C to 110 degrees C. So we're here at -5, and for this problem we're going up to 110. So at -5, the substance we have is ice. And we will have ice from -5 degrees to 0. And that's when that ice will start to melt. So that's this part of the graph. Next, we have to melt that ice. And that's represented by the flat part of that graph. Then once all of the ice has been melted, then we have water. And we start off with water at 0. And we will have water until we go all the way to 100 degrees C. Then we will need to vaporize the water or boil it. And then once all of the water is converted to the steam, then the temperature will go up. And in this problem, we only have to go up to 110. So after we vaporize it, I just have steam. And I have steam at 100 degrees C, and I will have steam until I get to 110, and that's just when this problem stops. That part right there, making the plan or the looking at the different segments, is probably the more difficult part of this problem. But once you have it, the rest of it's pretty easy. Anywhere you have a temperature change, we're going to use Q equals MC delta T, because that's how we can calculate heat with a temperature change. So that's here with the ice, Q equals MC delta T, Q equals MC delta T, and here with the steam, Q equals MC delta T. For the melting and vaporizing, going through those phase changes, we have to use another equation that involves Q. This is one that we have used before, and for melting, it's going to be Q equals MHF, heat of fusion. That is something that is given to us in the reference tables. For vaporizing, it's Q equals MHV. At this point, all I need to do is plug in the numbers. I included a chart here, which is pretty much a snapshot of what you have on your reference tables. You also have all of these equations. So now it's just time to plug things in. It's 5 grams that we're dealing with in this problem, and the mass will be the same, for the entire thing. So 5 grams times the specific heat of ice is different than water, 2.05 joules per gram degrees C, times the temperature change just for this segment. So I'm going from -5 to 0, so that's the temperature change of 5 degrees C. Again, I'm going to plug it in here. Mass is 5 grams, that's not going to change. And then my heat of fusion for water is given on the reference table, 334 joules per gram. And again, you'll see that the answers here will all come out in joules, which is how I can add them all together at the end. Here, 5 grams times the specific heat of liquid water, 4.184 joules per gram degrees C. And the change for this segment is 100 degrees C. Again, the answer will come out in joules. Mass, 5 grams, and then I need the heat of vaporization for water, which is 2260 joules per gram. And then this one, 5 grams times the specific heat of steam, which is 2.02 joules per gram degrees C, times the temperature change for this segment, which is 10 degrees C. Now all I have to do is add that all up together. So what I normally do is I just do it in at one time in my calculator. And so I would multiply 5 times 2.05 times 5 plus 5 times 334, so on and so forth. If you go through all that in your calculator, you should end up with an answer that's approximately 15,200 joules. And the only sig figs I really have to go off of is this mass up here, which has 2 sig figs, and it's over 1,000, so let's convert it to kilojoules, move it over 3 places, and so we're looking at 15 kilojoules for the amount of heat that it takes to take 5 grams of ice from -5 degrees C to steam at 110.